Now let's do a harder problem. You have 4 bars, 2 bars of length 7 and 2 bars of length 4. Make them move like so. You can see that each bar rotates in a plane orthogonal to its proximal bar. Now in this example, both the orientation and displacement of the bar depends on its proximal bar. Before, only the displacement of the segment depended on the proximal segment, but now it's both displacement and orientation. I guess technically the forearm orientation could depend on the upper arm orientation, but that's not how motion capture systems usually work. They usually spit out orientations of each limb independently, but sometimes you may need to solve this kind of problem. Before we start coding, we must figure out the organization of the coordinate systems. We have 4 bars, so we have 4 coordinate systems. Since each system depends both on displacement and orientation on another system, on its proximal system, we must set up 4 nested systems. System B is contained in System A. System C is contained in System B. And System D is contained in System C. All the bars run along the z-axis within their own local coordinate system. So we need to take this z-axis and rotate it in the xy plane of its parent system. Or in other words, we have a local nested coordinate system, and we must orient it so that its ijk vectors, well, more specifically, its k vector, is rotating in the xy plane of its parent system. Now within each parent system, the child system, the nested system, rotates at the top of the parent cylinder. Now the parent cylinder never moves within its own system, so this point will always be a fixed point along the z-axis, either 004 or 007, depending on which bar we happen to be working on at the time. So now you have the displacement and orientation of a local coordinate system within its parent system. So all you have to do is transform those points out of that local coordinate system and displace it accordingly, and then move down the chain to the next parent. We could do displacement like in the previous problem by using the last 2 vertices as the proximal and distal locations. But we don't have to. The reason we did that in the previous problem is because the orientation was in the global system after the transformation. So we needed displacement in that same system, in the global system. Now our orientation is in the local coordinate system. So you can apply the displacement in that same system. In fact, that is something you must always make sure of whenever you apply displacement. You must always ask yourself the question, are the displacement and orientation in the same system? In the previous problem, the orientation was in the global system, so we needed displacement in the global system. If we transformed all the bars in the global system, then we need the displacement in that same system. Reconstructing the animation is like how a kid reconstructs that Russian doll's toy. We start with the innermost system, System D. That system is in System C. Its orientation is a rotation in C's xy plane. Its displacement, System D's displacement, is 00C, where C is the length of bar C. A side note, if anyone is wondering why, when we are focused on System D, do we talk about System C, remember that question I posed by asking, is the universe tilted? Revisit that section if you're confused. After the orientation and displacement are applied, we now have bar D in System D. Now System C has 2 bars. It has bar D and bar C inside it. We do the same thing for System C and System B. we transform all the vertices from system C into system B and then displace it by 0, 0B, where B is the length of bar B. The only difference is that you had 2 bars in system C, so you have to transform and displace both in the same way. You do the same thing from system B to A, and then from A to the global system. Each time, another bar comes along for the ride.